today's sliding window median, the median is the middle value in so we want the middle value or the average of mean of two middle values. Okay, I mean, it's pretty standard. I think there was a very similar problem which said just do median of stream, and I guess this is almost the same. I mean, best would be if we would have some ordered data structure which could answer such queries in logarithmic time. There are such data structures such as strip, but I'm not gonna do that now because I don't know the rotations, so whatever. Instead, what we can do is, well, what we want to know, the middle element. So how about, or the middle two elements, so how about we split the window into two parts, the smaller elements and the higher elements. So we will have a min and max priority queue, and the median is the midi. Either we keep an invariant such that their sizes are the same, or the left one has one more. If the left one has one more, then the largest one from left half is the median, and otherwise the smallest one from right and largest one from left are the median. Their average is the median. So yeah, that's about it. And now problem is that, okay, we calculated for here and now we have to move. So how do we update it? We have to kick out some values, but in heap we can only kick out the top one. Well, here is where ordered sets come in. We put the numbers along with their indices, so we know how we can delete them, and we can also access the largest and smallest element. Easy. So, standard problem, standard solution. Two heap trick. Lower, or let's call it low and high. Let's do this. So let's immediately just iterate through the entire thing. And first we want to insert. So what we do is this. We insert everything into low because, okay, let's say we put an element that's supposed to go into the high part into low, or let's call it left and right, whatever, or low high. So let's say we insert element that is largest of them all, but we insert them into low. Well, it's gonna be at the end of low, and if so, we just move it to high, right? Now if it's supposed to be in low, great, it stays there. So we do low insert num_zi I. I don't want that, but okay. And now, well, there is for sure let's see, left one. Well, now there can be two more elements in there, or there could be one more element in there which is larger. Either way, we have to move something to the right. So if low size over high size plus 1 or low last element is higher than or equal to high just higher. If it's higher, then that's not great, because if we, let's say it's tight and suddenly we have element that's supposed to be there. No, we inserted it into high, and now what we want to see, we insert it there. So now a high has either the same amount of elements or one more element. So if we put an element into the other half, if it has more elements, well, they can either have the same number. So what can happen? Well, we put it to the other side. So either low R begin is over high begin, or low size smaller than high size. So in that case, we want to do low insert. So let's call it iterator is high begin, or let's call it the value. So auto value is this, and then we want to do low insert val and high erase value, and then what we want to do is remove. So if I over k, then we also have to do removal. If low count value is make pair out of minus I minus k, I minus k. So now if low has it, then low erase value, else I erase value. Now what do we want to do? If low size smaller than high size, then auto val high begin, low insert val high erase val. Else if low size over high size plus 1, auto val high begin. No, there is more in here. So low R begin, and then we want to do high insert val and low insert erase value. So I'm just doing some balancing, whatever, to keep the invariant. And then finally, if k, so if we have odd number of elements in the combined ones, then we want to do, so if I is larger than or equal to k minus 1, then if this, then we want to do low erase, no. So we have odd number one, so we just do ans, which I have not yet defined, ans pushback low r begin first, and otherwise we want to do ans pushback. So let's call this a double of low r begin first plus high begin first divided by this, and then we return answer, and then vector in, or sorry, vector double answer. That should work. What the hell? If not high empty and this or that. What do you mean by that? Let's push back low R begin first. What the hell? How is that possible, bruh? So if low empty or this. Okay, seems to work. Let's see. Overflow. So double this. Double this. Boom. Let's see. Okay. Okay, this does not happen. This does not happen, this does not happen, and then you put numSci in high. So low is not empty, but this one is higher than this one. What? I mean, I could put it there, but there could be less elements, so this is only validating. Right, I did the same problem a little while ago. Why am I fumbling this? What the hell? So many ifs, so disgusting. Whatever. I did something slow. It's K. Yeah, okay, that's slow. 2 heaps. That's what I'm doing. 2 multisets. Oh, this is way simpler. Remove outgoing. So if outgoing, is it from here, erase from here, insert incoming element, balance sets. I mean, this is literally unlock K, so who cares? What? Okay, I mean, I don't like that. Whatever. Okay, let's write up a solution. This is terrible, bro. Okay, we want to index kth element in an ordered set of size k. If we instead split this set into 2 sets, we can easily and keep their sizes as close as possible. We can easily find the median as mean of largest element in the first set and smallest element in the second set, or a single element, or just last element of, or the extra element if k is odd. Let's use 2 sets, multisets, or a set of pairs where each number is in a pair with its index to make all numbers unique. Each time we encounter a new number, we insert it into the top half. Then we check if is supposed to be in the first half, it's at the front of second half, and it's smaller than last element of first half, and if so, we correct it. Then we correct the sizes of the sets so that the first one is so that the size of first one is either the same or at most one larger than the size of the second one. Then we can get the median as described in the previous paragraph, or by getting the last element of the first half if k is odd of n log k, since we do note that for positions I over k, we first have to remove the outgoing element nums I minus k, and balance the sets before calculating the median to only keep numbers from the current window. Since we do O1 insert / remove operations and each takes, since we have at most OK elements in both of the sets. If we use an ordered set, space complexity, whatever, OK, since we have at most OK elements in either of the two sets. Okay, good night.